Welcome back to the Deep Dive. Today we're getting into something absolutely core to artificial intelligence, reasoning. I mean, it's fundamentally crucial, right? It lets AI systems adapt, make logical steps, and handle really complex problems. There's, a pretty strong agreement in both philosophy and AI circles that intelligent behavior really depends on this. So our mission for you today, our expert listener, is to really map out the journey of large multimodal reasoning models, or LMRMs. We're going to try and pull out the key advancements, the technical shifts underneath, and where these incredibly complex models are headed based on the detailed material provided. Yeah, previous analyses, they often focus pretty narrowly, maybe just on multimodal LLMs or language-based reasoning. But this deep dive, we're aiming for more of a coherent picture, tracing things from those early modular setups to the latest LMRMs, and even looking ahead based on, actual experimental results.
That's right. And we should probably start at the beginning. Stage 1, perception-driven modular reasoning. So in this initial phase, multimodal reasoning was basically built using separate task-specific modules. Think of it like, breaking the whole process down. You've got representation, alignment, fusion, and then reasoning. These systems mostly use things like CNNs, those convolutional neural networks, great for images, and recurrent architectures like LSTMs for sequences, all within supervised learning, right? So you had examples like neural module networks, NMNs, which would dynamically kind of piece together modules for vision and text, or hierarchical co-attention, HiCoat, using attention across modalities to link question word to image parts, and dynamic memory networks, DMNs, they brought in memory for reasoning over, say, multiple steps or video frames. Then the field took a pretty big turn towards pre-training and fine-tuning, especially with visual language models, VLMs. This basically pulled representation, alignment, and fusion together. Two main flavors emerged. First, dual encoder contrastive reasoning models, things like Vilbert and CLIP. They used contrastive pre-training learning by comparing inputs for zero-shot reasoning, so doing tasks they weren't explicitly trained on. And second, single transformer backbone interactive reasoning models like VisualBERT or Uniter. These fused vision and text inputs right inside a single transformer for, joint understanding. But, and this is key, the big limitation to stage 1 was that the reasoning was still largely implicit, often just boiled down to classification. So it struggled with being truly context-aware or generalizing well, even with better ways of combining modalities.
Okay, right. So stage 1 laid that groundwork, but it was kind of implicit, perception first. Let's unpack the shift then. If stage 1 set the stage, stage 2 brought a really pivotal change with multimodal large language models. This is where, for me anyway, it gets really interesting tracking those explicit reasoning steps. We call this second stage language-centric short reasoning, or think of it as system 1 reasoning. MLLMs, the multimodal large language models, they shifted things towards end-to-end language-focused systems, and they did pretty well on tasks like VCR and VQA.
They did, but there was a catch.
Exactly. Those early MLLMs, while promising, they were mostly just matching patterns on the surface level. They weren't great at, say, dynamically forming hypotheses. And that limitation, that's what really spurred the development of chain of thought, CUDA-T, and then pretty quickly, multimodal chain of thought, MPUT. This was huge. It made the implicit reasoning explicit, showing the intermediate steps.
Right, turning black boxes slightly more gray.
Precisely. And within MPT, we can sort of see 3 main approaches taking shape. First, there's prompt-based MPT. This is where carefully written instructions could actually elicit step-by-step multimodal reasoning traces. You had examples like VOT using scene graphs for video, or PCarity PT structuring reasoning for autonomous driving.
So guiding the model through prompts.
Exactly. Then second, structural reasoning. These methods learned the reasoning patterns directly, usually through supervised training. This led to more standardized, sort of stage-by-stage processes, like multimodal Cody's 2-stage approach, generate a rationale, then predict the answer. Or TextKite, with its 3 phases, image overview, coarse localization, then fine-grained looking.
Making the structure explicit.
Yes. And third, externally augmented reasoning. This is where you bring in outside help, advanced algorithms, or tools to make up for the model's own limits. So MMTOT used search algorithms like DFS or BFS, graph search, to find better multimodal outputs. And retrieval augmented generation, RAG, things like RAGAR, started using external multimodal evidence for tasks like fact-checking.
Leveraging outside knowledge or processes.
Right. But the important thing to stress here is that the reasoning, even with CUDA-T, was still mostly short-term, reactive, very much like that fast, intuitive System 1 thinking. It struggled with deeper abstraction or planning ahead.
Absolutely. And connecting that to the bigger picture, those very challenges of System 1 reasoning in complex real-world situations. Well, that's what pushed the field towards what we now call System 2 inspired reasoning. This puts the emphasis on slower, more deliberate, more structured thinking, moving past just reacting. Which brings us neatly to stage 3, language-centric long reasoning, or System 2. This is where large multimodal reasoning models, the LMRMs proper, start showing up. Models capable of deeper, more transferable reasoning, grounded more in cognitive processes.
So moving beyond just the immediate response.
Exactly. A key feature here is cross-modal reasoning. augmenting reasoning with multimodal info beyond just text. And this could happen using the model's own abilities or external tools. On the tool side, you saw models like VisProg and ProVQ that used program generation to tackle complex tasks like video QA. Visual Reasoner synthesized reasoning traces to train sort of plug-and-play visual modules. For intrinsic capabilities, models like TSIQ and Vocat were fine-tuned on special code datasets to reason directly about documents or charts in a single step.
Okay, so leveraging internal capacity more directly there.
Right. We also saw the rise of multimodal O1 models, taking inspiration from OpenAI's O1. Open source efforts like Marco 1 and LlamaBerry pushed reasoning beyond just think-answer. They adopted a four-stage approach: summary, caption, thinking, and then answer. And these often use search strategies like best-of-n sampling, beam search, or even Monte Carlo tree search. MCPS basically techniques to explore many possible solution paths.
Exploring the reasoning space more thoroughly.
Precisely. And finally, really gaining steam now is multimodal R1, bringing reinforcement learning into the mix. Using algorithms like DPO and GRPO, which essentially fine-tune models based on preferences or iterative feedback, has been really significant. Models like DeepSeek R1 and Eureka show improved planning, robustness, better generalization. They use agentic data and feedback loops to get better at exploring and optimizing complex reasoning pathways.
That's a really impressive evolution, moving towards more deliberate, longer reasoning chains. But looking at these System 2 LMRMs, where are they still hitting a wall? What's the fundamental limitation that makes us think we need something even beyond this, maybe a truly native approach?
That's the crucial question. Because despite all this progress with LMRMs, their reliance on a language-centric core still kind of holds them back in truly dynamic, messy, uncertain real-world scenarios. Current LMRMs, they often struggle with genuine omnimodal input handling vision, audio, text, video, all at once, seamlessly. And interacting robustly with external environments is still a challenge. You see this in benchmarks like Omna MI, where even top commercial models apparently scored below 20% on some really complex tasks.
Right, so the real world is just messier and more integrated than these models can currently handle smoothly. Which naturally leads us to this forward-looking idea from the source material: native large multimodal reasoning models, and LMRMs. The goal here is to tackle those limitations head-on with two key capabilities. First, multimodal agentic reasoning. This isn't just passive understanding. It's about proactive, goal-driven interaction. Think dynamic adaptation, like operator controlling GUIs directly or Search A1 actively pulling in external knowledge. It's about doing things based on multimodal input.
Acting in the world, essentially.
Exactly. And second, omnimodal understanding and generative reasoning. This is the dream of seamless synthesis and analysis across all modalities, using unified internal representations. We're seeing early steps here, even in smaller on-device models like Megra's 3B Omni or Mini Omni 2, aiming for real-time visual audio help.
A truly unified sensory input and output.
Yeah. But building these NLMRMs, it's not easy. There are major technical hurdles. We need those unified representations. How do you process and generate different modalities coherently? Maybe mixture of experts architectures are part of the answer.
Handling the diversity of data.
Right. Then there's scaling reinforcement learning for interleaved multimodal long chain of thought. Getting models to think using multiple modalities over extended steps, kind of like OpenAI's O3 and O4 Mini hinting at thinking with images.
Keeping that chain coherent across modality.
And the really big vision, models learning and evolving from world experiences. Continuous improvement through interacting with environments, tools, feedback.
Lifelong learning, almost.
And underpinning all of this is the need for data synthesis. We need massive amounts of high-quality, complex, interactive, multimodal chain of thought data to train these systems. That's a challenge in itself.
Definitely. So just to kind of wrap up where we've journeyed, it's been quite incredible. From those early task-specific modular systems where reasoning was hidden through the language-centric System 1 and System 2 models bringing explicit, longer reasoning, to now looking at this really ambitious vision of native LMRMs. The whole trajectory points towards AI that can genuinely perceive comprehensively, understand precisely, and reason deeply across all the ways we experience the world. Ultimately, developing LMRMs, it's not just about cramming in more data types. It's about fundamentally shifting towards a kind of machine intelligence that can truly adapt and interact with our messy multimodal reality, much like humans do. This really does feel like laying the groundwork for, potentially self-evolving systems, maybe even multi-agent organizations down the line.
That's a powerful summary. So, as you, our listener, think about this roadmap we've just walked through, consider the ripples in your own field. How will these evolving LMRMs being able to see, hear, talk, and act all together, how will that change the problems you're tackling right now? What entirely new challenges might they let us solve? And maybe just as importantly, what new questions will they force us to ask about intelligence itself? Feels like we've really only just begun to scratch the surface here.